Math 26, section 4.1. We're going to at least complete this section today, so it's a little bit long section. Talks about two major things here. One is called vector spaces, and the other one is subspaces. And we're going to learn about them, and then we're going to learn later on why are we learning those things. We're going to learn why. We're going to use them throughout the semester, like in this chapter, chapter 4, 5, and chapter 6. So to start talking about vector spaces, what is a vector space? That's the main definition of a vector space. A vector space, we define it as a non-empty set V, capital V, of vectors. So it's a set of vectors and two operations, addition and multiplication. That's what this parentheses means, such that the following axioms hold for all vectors u, v, w in V and scalars c and d that are real numbers. So a vector is called a vector space, or a set of vectors is called a vector space if those 10 axioms hold. You have 10 axioms hold. Or if someone say let V be a vector space, automatically means those 10 axioms that we're going to go over them now, they all hold. Okay, that's what it is. Number one, u plus v is in capital V in the vector space, and this is called closure for addition. Closure for addition. This means if you pick any two vectors u and v in capital V, so if you take u and v in capital V, then their sum will still be in capital V. That's called closure under addition. That's the first axiom. The second axiom is about commutative. It's commutative property of addition. It says if you take vector u and v, add them. If you add u to v or v to u, you should get the same result. Associative, it says if you add the last two vectors together and the result to the first is the same if you add the first two vectors together and add the result to the third one. Number 4, zero vector in V. So that if you take any vector u in V and add 0 to it, that will return vector u back. That's called identity. For any vector u you choose in V, u plus its opposite or inverse will give you 0. And cu, or c times u, is always must be in V. Again, c is a scalar. It's a real number. And if you have a scalar again multiplied by u plus v, you can distribute c times u plus c times v. The next one, number 8, if you have a scalar, the sum of two scalars times u, then you get cu plus du. That's also distributive property. If you have c times du, you can multiply c and d and the result by u. And the last one, 1 times any vector u, it gives you the vector itself, also identity. The other one was identity for addition. This is identity for multiplication. So if one of these axioms fails to work, then we conclude that the vector v is not a vector space. So again, I'm going to repeat the definition. A vector space is a non-empty set capital V of vectors and two operations, addition and multiplication. As you notice here with these axioms, we use addition and multiplication, such that those 10 axioms should hold or must hold. Let's look at an example. Is the vector V, which is a set of vector in the form x, y, so that or such that, so this column thing means so that or such that, it's given x bigger than or equal to 0, y less than or equal to 0. Is this a vector space? So how do you know this is a vector space? So let's say pick any one of these axioms. Usually at some point when you get used to it, you will look at them very briefly, quickly, and see, oh, maybe this one's not going to work. Let me test it out right away. Or maybe this one is going to fail to work. Let me test it. So if you want to test it for the closure, let's say, what you do, you take two vectors, call them x1, y1, and x2, y2, and add them together. What do you get? You're going to get x1 plus x2, y1 plus y2, as you can see. But notice, x1 is positive, x2 is positive, their sum is positive, like bigger than or equal to 0. This is negative or equal to 0, negative or equal to 0, so the sum is less than or equal to 0. So this holds. So it's the closure is fine. This still in V. Still in V. I tested the first axiom. What do you think? Do you think u plus v will equal v plus u? Yes, call this small u, small v. So if you do u plus v, that's going to be x1 plus x2 as we did, y1 plus u2, y2. That's going to be the same as v plus u, which is x2 plus x1, y2 plus y1. So it works. You can check the associativity. U plus v plus w is going to be the same as u plus v plus w. This will work out. On the actual paper, you should show steps that it works, even if you think it's really tedious, but still worth showing the steps. So we did u plus v equal v plus u. We did the third one. If we have the 0 vector added to that xy, you will get xy back, so that's fine. If you do u minus u, you will get 0 back. So if you do like xy plus negative xy, you will get xy as is plus negative x negative y. So that would be x minus x and y minus y. So you will get the 0 vector 0 back. So this is fine. How about 6? C times u is in V. Is that true? So C times u. Is this in V? What is C? C is a scalar. Any real number.
Well, it could be -1, right?
So someone said it could be -1. So let's see what is he thinking about. Keep in mind, let me write down again what V was. It was the vector xy under these conditions. Okay, that x bigger than or equals 0, y less than or equals 0. So what he's saying, you know, if you want to pick any vector, just so I can show you graphically what's going on. X positive, so you're going to go this way positive and y negative. So it's somewhere, I don't know where. Let's say, you know, positive, negative, somewhere. This is u plus v, let's say. U plus v, or x plus y, if you want to call it this way. So what happens is always, so if this is u, this is v, this is called resultant force, u plus v in physics. So if the u is this way, right, u in this is this way. So what is u here? U is, call it like x1, y1. And v is x2, y2. So what happens is c can be any real number. If you do 2, c to be 2, so you get 2u. What is 2u? 2u is going to be somewhere here. That's 2u, double that. But what happens if C is negative? So if C is -1, so you got negative U. Where's negative U? Negative U is constructed back this way, the opposite direction. Then what happens? This part here, this part, this is for this is our vector space V. This is where V is. But after we did the negative U, it went up to the different direction somewhere else. So we can say this is -1U or negative U. This is not in V. This is not in V. So since one of the axioms failed to work, so then V is not a vector space. I'm going to write VS for vector space. So then you don't have to check the other ones. How about is another example, this vector xy such that x times y less than or equal 0, a vector space. Is this a vector space? So what makes this problem a little bit more difficult, the earlier example, we knew x is bigger than or equal 0 and y bigger than or equal 0. Here, I don't know anything about x or y. I just know their product is less than or equal 0. Less than or equal 0, it means two things can happen. Either x bigger than or equal 0 and y less than or equal 0, or x less than or equal 0 and y bigger than or equal 0. So two cases. So how do we check? How about the closure? You can start step by step. So take a small vector u, x1, y1, and v, x2, y2. And which condition? Let's work on the first one. Provided x bigger than or equal 0, y less than or equal 0. So how do we check that out? Is this closure?
Well, the closure property doesn't hold.
Let's check. Is u plus v equals, so that would be x1 plus x2, y1 plus y2. So let's see what works. It says x bigger than or equal to 0. So this means this is bigger than 0, bigger than or equal 0. So this will give us bigger than or equal 0. You guys agree? And for the second case, less than or equal, less than or equal, so there's some less than or equal to 0. So does that work? That u plus v is okay? Yes or no?
Well, I thought if you chose like u is wait. Yeah, if u is 1, 0 and v is 0, 1, then u plus v is outside of v.
So u plus v is going to be 1, 1. But so he chose what we call.
Y2 have to be negative?
Wait a minute. So he chose what we call a counter example. So he chose u to be 1, 0. 1 is bigger than 0, and this is less than or equal to 0. So remember, that's what or equal to 0 means. It could be 0 or less, or 0 or bigger. So it doesn't have to be negative all the time. And that's what he did here. He took one of them to be 0 and the other one bigger than 0. So the choice is fine. But then when we did u plus v, it gave me 1, 1. So what's wrong with this? What's wrong with does that work? Does the closure work?
Well, y2 is bigger than 0. Isn't it supposed to be less than or equal to 0?
y2? He's not looking at these two conditions. He was just thinking about this condition by itself, this one. So he's trying to make sure that when you multiply x by y, you will get something less than or equal to 0. So if you look at the first counter example here, this is the x, this is the y. If you multiply them together, you get 0, which is less than or equal to 0. That's correct. And this is x0, y1. If you multiply them together, 0 times 1, you get 0, which is also less than or equal to 0. So the two examples meet the criteria, the given condition x, y less than or equal to 0. So when we added them together, we get 1, 1. So does 1, 1 work? So
no.
Does 1, 1, if you take this is the new x, this is the new y. If you multiply x by y, 1 times 1, you get 1. Is this less than or equal to 0? The answer is no.
No.
So what that means u plus v is not in the vector space V or capital V. So we say V is not a vector space.
Oh, so we can solve these questions only just with one example?
So in mathematics in general, if you want to prove something correct, let's say for this for the vector spaces, you have to prove that all the 10 axioms work. But as soon as you find an example, which we call a counter example in math, that makes one of those axioms fails to work, then it's not a vector space, and this means you don't have to check the other ones. You don't have to check the other ones. So you can stop here because you already proved it's not a vector space. And the question is asking, is it a vector space or not? Let me give you a different kind of example. Let's say polynomials, an example related to polynomials. Say Rn, is Rn a vector space where polynomials can be written as a0 plus a1t plus a2t squared plus all the way to a(n)(tn). This is a polynomial with degree n. A sub 0 is called the constant term. a0, a1, a2 all the way to an are called coefficients. So degree is n. a0 is the constant term. Just keep those in mind. Now, is this a vector space? Is a polynomial in Rn, means with degree n, is this a vector space? Well, to do that, let's check the closure first. Remember how we chose u and v earlier in the vectors. Here we choose two polynomials. The first one, call it the one we have, or the given one, all the way to a(n)(tn), and take q of t, which is b0 plus b1t plus all the way to bn(tn). The sum What's the sum? When you add them up, you add the A0 plus B0 plus A1 plus B1 T all the way to AN plus BNT, like that. Now, is this in V? Yes. Right? It's in the form like a number plus a number T plus da-da-da all the way a number Tn. How about if I want to check the commutative stuff? I need to find Q of T plus P of T. So that would give me B0 plus A0 plus B1 plus A1 T all the way to Bn plus AN Tn. And these two are the same. So commutativity is fine. Associativity is the same. You can check it out. It's going to work out. How about C times the vector? It means here C times P of T. So C times A0 plus A1T plus all the way to ANTN. Let's see if this is going to work. You multiply CA0 plus CA1T plus all the way to CANTN. And you can, if you like to group them, like this is a number, or scalar, like that. So this is fine. How about the next one? The next axiom. What's the next axiom? So we check the first one, commutative associativity. How about 0? 0, if you take 0, a 0 polynomial, and add it to the polynomial, do you get the polynomial back?
Yes.
Yeah, so if you take a P of T to be 0, and you have a Q of T, some polynomial, when you add them up, you're going to get Q of T back. So this is fine. So again, if you take P of T plus 0, or any polynomial plus 0, you get the polynomial back. How about if you do P of T, the next one is plus negative P of T, the inverse. Will you get 0? Well, you can show it if you have the patience to show step by step ANTN. So plus, multiply that by negative A0 minus A1T minus da-da-da minus ANTN. So that would be what? A0 minus A0 plus A1 minus A1T plus AN minus ANTN. So that would be 0 plus 0T plus all the way to 0Tn. And that would give us 0. So it works. How about the next one? C times U plus V. So C times P of T plus Q of T. If you do the work, you can multiply, right? You can multiply a scalar by the polynomial. So this works. How about if you have the C plus D times P of T? Can you distribute this out? Yes, you can multiply this plus D P of T. So this works as well. The next one, C times D P of T. You can multiply. If you multiply D times P of T and the result by C of T, you will get the same thing if you take CD and multiply by P of T. Believe it or not. And if you take the 1 times P of T, you will get the polynomial back. I think all of them are checked out. So this tells us that polynomials with degree n are vector spaces. Are vector space. Any questions for me about this? No questions? You can come up with tons of examples about vector spaces. I'm not going to do this, but maybe test this out. Is V composed of vector in the form x, y? What is x and y? What can, I mean, x and y, they can be any two real numbers, say such that x is a real number taken from real numbers. Is this a vector space? You can test it later and check, see if there's tons of examples to go over. But the idea here is to show step by step and know what a vector space is. Very important to keep that in mind. What else we need? That's about vector spaces. Now, how about the next idea here? Next thing called subspaces. So what's the definition of a subspace? What's the definition of a subspace? A subspace, again, a subspace of Rn is any set H, capital H, in Rn that has three properties. So think about this. This is the vector space V. This is the set H, the subspace. So three properties subspace has. First one, the zero vector must be in H. Okay, three things must hold. First one, is the zero vector. So 0 is the zero vector in H. That's the first one. The second one. So a subspace of Rn is any set H in Rn that has those three properties. The first one, the zero vector is in H. Now for every vectors u and v in H, we have their sum also in H. So this is the closure under addition. The third one, for every vector u in H and every scalar c, we have cu is also in H. Okay, so if you're done copying, we can say a subspace, to answer some of the questions, is basically a vector space which is, say, a subset of a larger vector space. So if that makes sense. So in summary, it's a subset of a space. It's a subset of a vector space. Okay, now we can move on. So let's say we are asked to prove a set H given as A to A. The earlier one I gave you, I told you to try is XX. This one I changed and made it A to A, where A is a real number. Prove this is a subspace. So when they say prove means it's really a subspace. Don't try to find an example to make it fail. So three conditions we need, or three properties need to be checked out. The first property is the zero vector in H. Is the zero vector 0, 0 in H? How do we check that out? Well, this can happen if, because A is a real number, we can set A equals 0. Then the A to A, it becomes 0, 0, which is in H. So the first property is fine. It worked out. Now, if we take two vectors, okay, if we take two vectors in H, so we say if you say A to A and V, B to B, so I took two vectors, then what is their sum? Is their sum in H? U plus V. For U plus V, you add A plus B and 2A plus 2B, which can be rewritten as A plus B and 2 times A plus B, which took the same form, something and 2 times the same. So that's an H. So this worked out. So how do we check the closure? Under scalar multiplication. So we let U be in H and C scalar. We need to test if CU is gonna be in H or not. So by the definition of H, we can take U to be A to A. Then CU, it's C times A to A. You can multiply the C in, CA and 2CA. So notice what we have. We have something and 2 times the same thing, which also an H. So that shows me H is a subspace. So again, only 3 properties you need to check out. And now let K be the set ABC in R3 where A times B bigger than C. Is K a subspace of R cubed? So with this one here, let K be the set of vectors A, B, C in R3 where A times B must be bigger than C. Is K a subspace? So always ask yourself, what are the 3 things that I need to check, or 3 properties? Is the 0 vector 0, 0, 0, is this vector in K?
No.
Well, can we take, if we take ABC, all zeros, all these zeros, then we got, you know, the 0, 0, 0 for the ABC, but is the condition A times B bigger than C is satisfied? Well, let's see. If A is 0, B 0, that's 0. 0 bigger than 0. Oh, that's not true. So since one of the properties failed to work, then K is not a subspace. Then K is not a subspace. So as soon as you find out at least one of the properties fails to work, then it's not a subspace. Note, the vector space R2 is not a subspace of R3. It's not. However, there is, I call it, a copy of R2 sitting inside of R3 that is a subspace. A copy coming from R2, not R2 itself. For example, let's say A, B, and 0. Let's say this. That's this one where A and B are real numbers. This is a copy from R2 because there's no Z. So this is a subspace of R3. You can test the three properties. Also, let's look at is a line that does not pass through the origin. Is a line that does not pass through origin a subspace of R2? So we need to check if a line that goes through the origin, does not pass through the origin, is a subspace or not. You may pick any line, say this line. Now we need to check three, because it's subspace, three properties. Is the zero vector, is it in there? So how do you check?
It's not on the line.
It's not on the line. So what is the zero vector here? Is 0, 0. So we see this is the zero vector there. The answer is no. We can stop here saying it's not a vector space. Again, what are we testing? Those three properties. The first property says, is the zero vector in H? Okay, so H here is basically the set that contains all straight lines that do not pass through the origin. And when we say zero vector 0, 0, say 0, 0, you know, that's just the point itself there. And we can look more just so you see more examples of this. Same example, is it closed under addition? So if you take two vectors u and v, okay, the first vector is on the line. This is vector u, and you take a vector v, let's say this one. Where's u plus v? You complete the parallelogram. So u plus v is this. Notice u plus v is not on the line. Call it line L. So u is on L and v on L. But u plus v is not on L. So three things we need to check. Is the zero vector in H plus the second one, is it closed under addition? And the last one, scalar multiplication. Is it closed under scalar multiplication? Let's test that out. I know you don't have to do it all, but just in case, if you like to see how to test them out. So we need to see u times c times u. Is this on the line or not? So like if you do double, let's say 2u, if the u goes from O to this point, 2u would be double that. That's 2u. Notice it's not on the line. Not on the line. So it fails the three conditions or the three properties here. So definitely not, it's not a subspace of Rn or of R2 here. We may move on now to a theorem. Let v1, v2, all the way to vp be vectors in Rn. Then the span of these vectors, v1, v2, all the way to vp, the span is a subspace of Rn. In other words, we are saying that the linear combination, if you remember from previous sections, the linear combination is a subspace of Rn. That's what the span means. So the theorem said, if we take vectors v1 to vp in Rn, then the linear combination of those vectors is a subspace of Rn. And we're gonna prove why this is the case. So we can write, for simplicity, we write H to be the span of these vectors v1, v2, all the way to vp. And the first one is the zero vector in H, right? To check if it's a subspace. Well, what we can do, we can write 0v1 plus 0v2 plus all the way to 0vp. This is equal to zero vector, right? If you add them up, you get the zero vector. So that's in H. That's what linear combinations means. it's A1 V1 plus A2 V2 all the way to AP VP. So you can take all these A's, A1 to AP, to take all of them to be zeros. So if you do it that way, you'll get the zero vector. So that proves to us that zero vector is in H. So that's the first property, is satisfied. Now we take two vectors, U and V, in H. Okay, is their sum U plus V in H? So is it closure under addition or not? Will close under addition or not? Let's see if we can prove it. So we take vector U, write it as C1 V1 plus C2 V2 plus all the way to CP VP, and vector V, D1 V1 plus D2 V2 plus all the way DP VP. Okay, here for some scalars CI, for some scalars DI, then U plus V. If we add them up, you can add C1 plus D1 V1 plus C2 plus D2 V2 plus all the way to CP plus DP VP. So that shows me it's a linear combination. That's what linear combination is, of VI's. Yay. So U plus V is in H. So that proves the second property. Next one, let U in H and C be a scalar, any real number. We need to see the scalar multiplication. Does it work or not? Is CU in H? To do that, C times U equals C. What is U? C1 V1, C2 V2, all the way to CP VP. So multiply C1 V1 plus C2 V2 plus all the way CP VP. Then CC1 V1 plus CC2 V2 plus all the way CCP VP. And notice this takes the form of a linear combination as well. Linear combination of VI's. So this tells me CU is in H, and hence H is a subspace. So H is a subspace of Rn. H, which means is the set of the spanning of the vectors. Keep in mind the set 0 is a subspace of Rn that contains only the vector 0. And it's very easy to prove it's a subspace. You know, if you want to prove them, we have the 0 vector, which is, that's what it is. It's already in H. It's a 0 vector in itself. And then if you take two vectors U and V, from this set, from the zero vector set, then this means both u is 0 and v is 0. So their sum is going to be the zero vector z. So this works, so this is in H. And the third one, if you take c times u and u is 0, you get c times 0, that gives you 0. It worked. So since the three vectors are done or set this way, then the set of 0 is a subspace of Rn. Also, I want you to know the set Rn is a subspace of Rn itself that contains on every vector in Rn. And to see this, it's very easy. Or let's say the zero vector, if you take a zero vector in Rn, it's going to be in Rn, right? If you take any two vectors in Rn, their sum will be in Rn, so it's closed under addition. And the third one, if you take C and another vector, then from Rn their product would be also in Rn, so it's closed under scalar multiplication. So that's what subspace and vector spaces are about. And then you're gonna, in all the subsequent sections, you're gonna hear us saying subspace, vector space, subspace. So vector space means it satisfies the 10 axioms that we showed you. And subspace, it satisfies the 3 properties that we have been working on. So that's what it means. So every time they say let V be a subspace or let H be a subspace, it means automatically it satisfies the 3 property: close under close under addition, close under scalar multiplication, and contains the 0 vector. 3 of them. If they say let V be a subspace, vector space, it means it contains or it satisfies the 10 axioms that we have. 10 axioms.